Hello and welcome to another Practicalli study group. Thank you very much for joining me. My name is John Stevenson, and today we're going to have a look at Advent of Code, which is a yearly challenge, coding challenge for you to try out. You can do it in any language you want, because we're practically discovering the functional programming. We're going to do it in Clojure, and we're going to have a look at day one, and we're going to try and solve it in a few different ways as well. Along the way, we'll look at something that I think I've briefly touched on before, something called transducers, which sounds fancy, but it's quite a nice abstraction over the ideas we've come across with reduce and with comp functions as well. So I'm going to try and make it as simple as possible to explain, and point you to some more resources where you can go and learn more about transducers as well. Okay, let's have a look. So as usual, the website has all the details, has all the links to all the videos, and also the books I'm working on as well. I've just done an update on Spacemacs for that. You can reach out to me via the Clojure Slack community on the Practicalli channel. There's quite a few people that have joined that recently, so thank you very much. You can also get if you don't have a login, you can get a free login for that just with this link below. And if you want to support me, then obviously subscribe to my YouTube videos. I think my charity ride is closed now, so I've met my target. So thank you very much for everybody who's contributed on that. You can also sponsor me financially via PayPal or GitHub, or just say nice things about me wherever you are, and that will keep me motivated as well. Thank you very much. Just one thing before we start, just a brief advert. So we're organising another Clojure Bridge London event. So in end of February, on the 21st to 22nd of February. These are Americanized dates, I'm afraid. We're trying to get that updated so that they have a more universal date format. But yes, this is like the 21st and the 22nd of February in 2020. Oh my god, it's nearly a new year already. And Signal are hosting this for us. So if you haven't come across Clojure Bridge before, it's a way to help unrepresented groups get into coding or get into specifically Clojure. So we get about 50% of people who've not really started coding yet, not commercially anyway. And we get some people who started coding in their first language, but they're curious to learn about Clojure as well. And so there's a whole website with information. We go to clojurebridgelondon.github.io. There's some more information there, some more background in it, and also the learning paths as well that we cover. And if you'd like to volunteer to coach people, then we're always looking out for the people to help out in that way. So you can actually go and look at the learning paths and see what kind of things you'll be coaching people through. Okay, if you've got any questions, you can ask me about that on the Practicalli channel. There's also a Clojure Bridge London channel on the Clojure Slack as well. So if you go same Slack community, and you just do hash Clojure Bridge-London. Okay, adverts over. Let's get on with Advent of Code. So let's make that bigger. Woo, make it big. So I've already logged into this, but you can log in with your GitHub or any other kind of ways to identify yourself. So you've got Google account, Twitter account. I just use my GitHub account. And you can log in because you get a specific set of data to work with. So when you start doing the challenges, then they give you your own unique data set to work with, and then obviously you've got your own specific answers that is going to be generated from that. And you can see that it also tracks how many challenges you've done. I've only done one, unfortunately. It's a busy week. But then every challenge you complete, you get a star. And each day, these are representing the 25 days up until the holiday, and it's every day has 2 parts to the challenge, so you get 2 stars for each day. And I think it makes a picture as you fill in the days, and it shows you the time for when the next one's actually going to be released as well. Okay. And so it's just there's you go and click on each day, and it gives you a blurb of what the challenge is all around. So here we've got Santa. He's become stranded at the edge of the solar system. It always happens this time of year. And we've got to align his warp drive and safely return him back to Earth so he can deliver presents for Christmas. And so the way we do that is by solving puzzles. And the first puzzle here is this Tyranny of the rocket equation. So we actually need to figure out an equation to be able to fuel the rocket. Because as we're kind of getting as the elves are loading Santa into the spacecraft to prepare it for launch, we're doing our go no-go checks. You may have seen this where if you've been watching a NASA launch, they check to see if all the essential parts are working. And one of the most essential parts is to have some fuel. If you don't have any fuel, your spacecraft is not going to go anywhere. So we need to fuel the spacecraft, but we need to do it so we'll actually take off. So we need to know how much fuel for a particular mass. So it's got a whole bunch of modules, and each module has a mass. So we need to work out the fuel required for each of those modules, and then add them all together, and that's how much fuel we actually need to put in there. And they give us some examples, so you could actually take these examples and put them into unit tests, or just have them as part of the REPL, and just put them there as little tests you can do in the REPL as well. It depends if you want to do unit tests for this or not. Obviously, if it was production code, you'd be doing unit tests, obviously. And so it's saying for a mass of 12, you divide by 3 and round down to get 4. Then you subtract 2 and you get 2. So it's like it needs 2 units of fuel, and 14 needs also 2 as well. And mass, so the larger the mass is, obviously the larger amount of fuel you need. And so we need to go and calculate the mass of each module, and then we add them all together to get the fuel. So it's given me the data already, and I think it's the same data for all of the challenges, and so we need to then come up with a single value, which I've done here. So obviously this works for my data set. Your value will be slightly different because you'll get a slightly different data set. And so the data is, so I've just basically put this into a project. So let's have a look at that. So I created a project using the clojure-cli tools. Again, you can use Leiningen or Boot or any other tools. And I've just basically used the Clojure CLJ new tool with the Clojure-cli tools. And this is going to create a new application. I could have done it as a library, but my idea was to be able to run it and generate all the results. And so I'm going to put it into Practicalli Advent of Code 2019, and then have specific files for each day. So each day is going to have its own namespace, and I'm going to put both parts into that namespace. So I'm going to organize it so it's very easy to just drop in to each of the individual kind of days and see what the results are. And so I've got that here. So if we actually look at the tree, because I'm in there already. So it's just created this project layout for me. So I'm using deps.edn for the configuration file, and that's just got Clojure in there. There's nothing particularly exciting in there. There's also a test runner in there just in case I did write some tests. Yeah, and then we've got this main Clojure file that we're going to work with. But I've also added this. Okay, so we've already also added this data file in there as well, and I'm going to put the puzzle data in there specifically. So we go to our editor. Let's just go up. I'm going to make that just a little bit bigger. There we go. I've got a new setup, so I'm just tweaking it a little bit. There we go. So I put so we've got the namespace in here, and I've required the data namespace as well. So if we have a quick look at the data namespace, it is just, I've just basically copied all the values into into a vector. You could write a little function to just pull this in from a text file if you wanted to. That would make it more reusable for other people. But as I'm just doing this for myself, I've just basically pasted I just essentially hard-coded the puzzle input into here. So each of these is representing the mass of a particular module that makes up the spacecraft. So there's quite a lot of them there. So I've just put them in its own namespace just to keep it out of the way, so I can then focus on just the code itself. So we've got the description, we've got the tests we can run to see if we've actually got the right answers. And then we have to work out how to actually calculate the fuel. If you have any questions as we go along, please feel free to put them in the chat. I'll try and keep an eye on them and not get carried away with my coding. So I've got a function called fuel for module, which will, given a particular module mass, it's going to go and return like an integer value for how much fuel we want. We're only dealing with integers, we're not dealing with floats, so we can't have like a point something. We can't have like 3.4 units of fuel. We have 3 units or 4 units. And so the way we calculate it is we divide the mass by 3, and then it needs to be rounded down to an integer and then subtracted by 2. So divided by 3 is quite easy, but this is going to generate a decimal number rather than the whole number, unless the number we're dividing by 3 is actually divisible by 3. And so we would need to convert this to an integer, and then we would subtract 2. So a simple way to do that actually is just to use this function called quote, which we've done before. So this will actually just divide the value of module mass by 3, but it'll only take the whole number part of the answer. So if we divide, if module mass is 4, and we do quote for 3, then it's going to return 1, because 4 divided by 3 is 1 with 1 remaining. So we're actually going to just going to drop the remaining value and just return the whole value. And then so effectively we get our integer without having to do any rounding, and we don't have to worry about rounding errors in that way as well. There are some maths ceilings and things like that, functions you can use to do rounding, but sometimes they can be a bit lossy. So this is kind of the safest way to actually do a rounding down to the lowest value. And then we take 2 off the unit of fuel, and that's our resulting fuel that we need. And so then because we have multiple fuel, then we also need to go and actually work over each of those module values that we had in here. So we have to basically apply this this function we've done to calculate the fuel. We have to apply it to all of those functions, and then we have to get the total as well. So we can just if we've got, have we got that running? Oh yes, I'm already running my REPL in here. So I can call this with one of the tests. If I do fuel, oops, can't type fuel for module, and if I give it one of the tests that we've got here, so it says 14 is going to return 2. So if we pass this a module mass of 14, oops, and then we get 2. So that seems to be working okay. We can give it another value. Let's give it the value of 1076. So if we do, we paste that in and delete that, and then that was it. We get the value here. So we should return 33,583. Yay, there we go. So that's working okay for the given tests we've got. So that sounds promising. So obviously we could write unit, you can make these into unit tests, just using clojure.test library. Let's just comment these out for now. And so we need to basically solve part 1. We need to basically add up all the results after we've mapped. So we're going to map fuel for module, which is a function we've just written, over the puzzle input. So we're passing puzzle input as an argument. And so we map it over, and then we get the individual results. And so if we did, if we just grab this, boom, 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 and then we just change that to, so this is in the data namespace. It's called puzzle input. So if we evaluate this, then we get the fuel for all of the modules there, so the individual ones, and it's quite a lot, so it's not all showing on the screen, but we can then just add them up. So if you've got a collection of numbers you want to add up, then you can, simplest way to do that is just do reduce plus and add them all together. So that's what we're doing here. We're reducing with plus the result of mapping fuel over our puzzle data. So then we can just basically solve part 1 just by evaluating that. What did I do? Oh, what have I done? What have I done? Oop. Oops, wrong page. Let me see. I've probably got a typo in somewhere. Oh, okay. Oops. Yes, I didn't evaluate my function. Sorry. It is Sunday morning after all. Ooh. Ooh, there we go. Oh, I'm back again. There we go. Yes, I forgot to evaluate this. Wrong window. There we go. Yes, unfortunately, I can't. There are some marks to show me that it's been evaluated, but I just can't see them on this. It's very difficult to see them on. They're right there, but they're so tiny and so blended into the background. I can't see them. Yeah, so now it works. Now I've actually evaluated the function definition. It actually works, which is nice. And so that is giving me the result there, which I believe is the result I put into the web page. Yeah, 3372463. So that's part one solved. So the first part is usually quite easy, or relatively easy, and then the next part becomes usually more iterative in nature, more recursive in nature. So it usually requires a little bit of thinking about it. I quite like it that way because it gives you a quick hit of success to get the first part, and then you have some idea about how to do the basics, and then you expand that problem into something a little bit more complex. And I think these challenges are quite good for helping you think in a functional way as well, because there's a temptation to just do them in a very procedural way, and so it gives you an opportunity to try out things in a more functional way with Clojure. Okay, no questions on part one so far, so we'll leave it as that. I was going to put it into a main function, and then I could call it from the command line as well, but I'll leave that for now. And then we've got part two. So what we've done so far is check for how much fuel we need for each module, because each module has a weight, has a mass, and the more mass that we add, the more fuel that we need. But if we're adding fuel, the fuel itself actually has a mass. So then we actually need to say, well, okay, well, if we add like 10 units of fuel, then that fuel is going to need some fuel to be able to get the spaceship to actually take off. So for every fuel that we add, we need to also add some fuel to take care of that fuel. And it's the same calculation. So we're still divided by 3, we're still rounding down to like a whole number, and subtracting 2. And so, but once we get down to a mass of, I think it's like about 5 fuel, then we don't need any more fuel for that. So there's a certain amount of fuel that we can add without adding fuel for that. Otherwise we'd be going on forever and ever. We'd be going on for infinity. We'd never actually be able to add enough fuel, because there'd always be a little extra to add each time we wanted it. So that would be infinity, and our computers don't handle infinity just yet, or possibly ever. So again, there's some more examples here. Where are we? There we go. Oops. So if we've got a module mass of 14, it requires 2 fuel. And there's if we divide, and the fuel itself doesn't require any fuel, because if we divide 2 by 3, then it's less than 0. And then take away 2, then it's less than 0, so it would be negative fuel. We don't want to take off fuel, although I did actually manage to do that in my code at one point before tweaking it. And then so we get the total fuel down to a limit. So if you think about it, then if you divide 6 by 3, then you get 2. So anything less than 6 definitely doesn't need any fuel, and in fact 6 doesn't need any fuel either. Yeah, so if you've got 5 fuel, so if you've got something that requires 5 fuel, then no further fuel is required. And so there's a few tests here that kind of give you the output of what they expect. So for like the individual modules, and then we can use that to test our algorithm, and then see whether we're on the right lines for that. To see this kind of thing in action, there's actually somebody did a really nice approach to this. They actually used Quill to visually represent what was going on. So there's a link here in the code, which is on the code. All the codes actually on this Practicalli Advent of Clojure code repository. So there's a link in that code here to this Quill, and I'll put this in the YouTube notes as well. And so basically this is the same thing. It's generating fuel for mass, and it's doing it for all the masses, and it's also getting the deltas as the extra fuel for the fuel. And if we run this, and I'm going to hide my extra bits there. If we run this, you can see it's actually just generating the fuel, and for each module there's the fuel required, and then the fuel required for that fuel, and so on and so on and so on and so on. So you can see visually see what kind of thing you're actually trying to calculate. And I thought it was just a really nice example of how to do that there. And it also shows like how you can do some nice, interesting, some basic visualization in Quill. So you can use this for like some basic data science stuff as well. Okay, I'm going to close that for now. Boop, boop, back to there, and back to the editor. There we go. So how are we actually going to solve this? We could I haven't done a loop recur thing for ages, so I thought I'd just start right back at the very basics and do a loop recur. And so we're taking in our module mass, so we're still just working out the fuel here for a specific module. We're not trying to do all the modules yet. We can just do a recur over that once we've got this module for calculating the fuel and the fuel for the fuel. So we've got a loop here, and we can have a mass that we get from the module mass. So this is our starting mass. So this is the actual mass of the module itself. And then we work out the fuel for that. So this gives us our standard, the same algorithm we were using before. And then we're going to have a counter. We're going to keep the total amount of fuel that we want as we go through. So this is just going to add this up. And so then when we loop through the different levels of fuel, because each time we're going to get a value for fuel based on the module mass. And the first time this is the mass of the module, the second time is going to be the mass of the fuel, and the third time is going to be a mass of that fuel that we've just added for the previous fuel. So we're going to go round and round and round and round, and then if the fuel is 5 or less, then, although that probably could be 6, but 5 worked, so that'll do for now. So we're going to check to see if we have we're only adding fuel that doesn't require any more fuel. If that's the case, then we can just add the total fuel to the total and just return that value. To actually do the loop, then we need the recur statements. So we're going to pass back into these 3 values. Firstly, we're going to pass back the fuel. So the new mass here for the second time round is going to be the fuel that we've just added. So we've calculated what the fuel is here. So this is fuel we need to add for this module, and then we need to pass that back in as new mass that we need to calculate fuel for. And we are passing back the fuel that we're going to require, and then we're going to pass back the total each time as well. So we're going to go round and round that loop. So if we do if we put this into debug mode, you can see that's happening. So we've got a couple of tests here that I'm going to run through. So just do the simple one first. So just evaluate this. It allows us to step through the code so we can see exactly what it's doing. So we're passing in a module mass of 14. and then we calculate the fuel for that module mass, which is 2, which is right because that's what it said above. Then the fuel is less than 5, so we just add the fuel to the total, and we get 2, and then we return that as a result. So that's simple. So we don't actually have any fuel for the fuel, but in this case we do, because we have more mass. So we're passing in the module mass, we calculate the fuel for the module mass, and there we go, and we pass that in. That is bigger than 5, so we do need to add some fuel for this fuel that we're adding. So we go around the loop, we recur, we set the fuel to be the new module mass, and then we calculate the fuel required for that fuel, and we add the fuel from the module mass to the total, and then we pass that in. And then we go around to, we're adding, so this time we're adding 216 units of fuel, which is still bigger than 5, so we still need to add some fuel for that fuel. So we go around the loop again, and this time we're going to add 70 fuel, so we're adding 216 from the previous one. We get our running total. We see that 70 is still greater than 5, so we keep going round. We get 23, 21, add that. So 21 is still higher. Boom, 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 boom. And we get 5. So we've got, adding 21 units of fuel means that we only need 5 units of fuel for that 21 units. And we don't actually really need any more fuel for those 5 units. It's close enough. There's an error of margin there of how much fuel we need, so we can actually just safely skip that. So that's true. We can break out. So this if condition is controlling when we break out of our iteration. And so we're adding our total up to get 966, and that's our result. And if we go and look at the 1969 thing in here, yeah, so it's adding 966 is the result that it gives us already. So we know that it looks like we're on the right lines for this, for generating our total fuel for the module and all the fuel that we're adding as well. So now we've got that. And again, there's probably much nicer ways to actually write this, but we can use this function. We can abstract this away at a later date, but we can use this function, this total fuel for module. We can basically map that over our data to get all the individual results, and again we're just reducing by plus to add them all together. Let me just evaluate this to get rid of the debugging, and then we can just run this just to show you it's all working. There we go. So that's the result for all of the fuel. So if I go back to day 2, part 2, day 1, part 2, and then that's the answer we put in there, and we got 2 gold stars. Yay! So that's good. But we can do better. We could go back and improve the loop recur and make something a bit more abstract. So the nice thing is, I mean, you can take these challenges as something quite competitive and just try and be like first. You get a few extra points for being the first to solve a particular puzzle. But you can also take the more hammock-driven approach, where you actually go, you solve it, and then you go away and think about, well, what other ways can I actually solve it as well? So that's what I did in the other. So I started looking at different ways to do that, and I saw somebody doing an interesting thing with transducers. So I kind of did my kind of version around that. And it's a nice way to kind of recap for myself what a transducer actually was. And it's something we haven't actually covered, so I'm going to go into a little bit of detail just to kind of give you a gentle introduction into what transducers are. It sounds a big fancy word, but it's actually it's relatively simple. If you're comfortable with reduce and comp, then kind of the basics of transducers are fairly easy to grasp, I think. So transducers are a way of applying an algorithmic transformation, which sounds like a big word, but it's basically an algorithmic transformation is just a kind of function that you can apply and it's basically a recipe on how to transform some data. So this kind of map total function, total fuel for module, we could have that as a transducer. And a transducer doesn't really know or care what data it's going to get. We can actually delay. We can write the code and evaluate it, and it will actually wait until something gives it some code to work with. So it's kind of returning. It's what's called, when you call it things like map and filter and so on. There you can actually get them to return a transducer, which is kind of like returning a function definition, and then you can run that with some code. Sorry, we can run that with some data and get specific results at a later date using the transduce function. So it's basically just an abstraction on top of reduce and comp. Essentially, you can basically do a map total fuel. Let's do this. I've got some other examples here. So we can create map total fuel, and that's a legal kind of that's a valid function. And so you can see it's actually returning a function, a pointer to a function that we can call. And so we're not actually giving it the data here. The data is actually missing, and we can use that as a later date somewhere else in our code. But we can just set up this generic way to transform a piece of data that is our puzzle input into the answer to solve the challenge. This is what we're trying to do. So it's a nice way to kind of delay that, and it's probably a little bit overkill for this, but I think this is a nice example of how to kind of get starting to think about transducers. So we did previously look at reduce and how it iterates over a function of a collection, and we've kind of seen this already with solving the challenge already. So this is just a much simpler data set that we're doing it over. So we've been reducing over the results of mapping total fuel over the module data, and here we can just reduce something over. Essentially all we're doing is just reducing this collection down, this collection of values. We're reducing it by applying plus to each of these values in here, and so just essentially adding them together. We could also do multiply as well, and so it's reducing them down to a particular value by using the multiply function. And we can write our own algorithms, our own little functions we want to apply, and we can get quite convoluted, quite complex things there as well. So we've got a nested a nested expression, which is our algorithm. So we're going to take our data set, we're going to map this little function, this inline function we've got here, and that's going to add 7 to each of the values that are generated by range. So range is our data set. So rather than typing out 100 numbers, I'm just generating them. And then I'm going to map this function over each of those numbers to just add 7 to them. And so then we can see that if we do that. So if we're mapping +7 over everything, then we're just adding 7 to everything. So it's just basically having offsetting our range of numbers by 7. There is actually an easier way. We can just put that as the starting value, but then it wouldn't give us 100 numbers. So this allows us to kind of set an arbitrary starting point and still get 100 numbers generated. And then we are going to, from the results of map, we're going to then we're going to filter them by using odd. And so we just get all the odd values. And so that will give us just the odd values there. Let's see. There we go. Boop. So this is the result of filter. So we've dropped 8 and 10 and 12 and so on and so on. We're just getting the odd numbers there. So we've got 50 numbers, and then we're just reducing to get the final result of adding all those things up together. So this filter odd map, this thing without the range 100, that is our reducing function, and the reducing function term just means it's a function that we pass to reduce. It's kind of as simple as that, really. So it's just something we can use with the reduce function, and we can take this example and abstract it, so make it more generic. We can apply it in different places, and we can use different reduces with it as well, and different data sets, because here we've got the data set embedded into that. I mean, we could pass that as an argument in a function, but we can use this idea of transducers to kind of simplify it as well. So we're going to have this expression where we're going to compose the results of map 7. So we're going to map this function to add 7 over our data set, and then the results of that we're going to filter with odd. So we'd actually build up a nice little so-called pipeline of transformations that we can build. We can just keep on adding more and more of these to that to build up our algorithm, and then we could just represent that with a name, in this case the very unimaginatively titled name of algorithm. Obviously we'd put something in a bit more meaningful in there, and then we can use that algorithm to transform a particular data set, and we can use transduce to do that. So we can see that we can actually define map and filter without having to specify the actual data they're going to work on. So normally you'd kind of like expect, if you're just defining this outside of comp, you'd want some data, but this data that would go here is actually going to be passed to algorithm when we transduce. So you can see here we're actually passing we're passing the data here from range, and we're going to add everything up once we've applied the algorithm to those values. So we can see we can build up this algorithm without having to specify the actual data. We still need to know the shape of the data. These functions are still going to need to be able to work with each other, but we can build them up and build our algorithm up. We can also, while we're testing, while we're developing this algorithm, we can comment these algorithms, these particular parts out. We can see how it's actually working in that way. Oops. So we can change the results of these combined transformations just by adding and removing them. And then once we've got our algorithm, then we can use the transduce function, which is very similar to reduce. except that we're taking this transformation algorithm that we're doing, and so this is going to be applied to all the data, and then in this case we're just reducing all that data by using the plus function, and so it gives us a grand total of 208. So we've seen here when we did reduce, so this is the same as this, because if we do this we get a result of 2800, and if we then run this algorithm here, as you can see, we're getting a result of 2800. It's the same, we get the same results because we're applying it to the same algorithm. We're just kind of separating the algorithm from the actual reducing function, so we could actually do this elsewhere. So you could have a whole series of algorithms that you're going to use of your data, and then at different parts of your different functions you can transduce them and reduce them down into values, and then just select the different algorithms you want to be able to define how you want to transform that data. And we can also set a starting value as well. So here we're starting like at -1000, so it's basically essentially taking off 1000 from the results as well. So sometimes that's quite useful too. So there's another example here. So here we've got a very simple add values. And here we're basically using multiply to reduce them down. So we're going to multiply each of the values together after we've applied the add values transformation to each other. So it's going to, add values is going to take each of these elements of data in turn. It's going to take 1, and then it's going to pass that to this function to get 8, and go through, and then 2 to we get 9, 10, 11, 12, and so on. And then we're going to take 12. Well, we only actually got 5 values here, so it's just going to take the first 5 anyway. But it would take no more than 12. And then we're going to, once we've gone through our add values algorithm, then we can reduce all those values by using the multiply function, and we get our results. So hopefully that gives you a few ideas about using transduce. You don't have to, it's not an essential tool to use, but it can help with some optimizations because you're not defining any local names or instances here as well, so it can be more efficient under the covers. It can run more in a more performant way, and it's a nice abstraction to apply especially when you're refactoring your code. It's probably not something you would start off by writing, but if you see you've got sort of nested, you've got a whole bunch of nested functions in here, and you can see that these are all these functions will return a transducer, and then you can see, well, okay, well, I could compose them together. You've already got a nice abstraction there, and then you could say, well, okay, I'm going to reuse this transformation, these set of functions that define the data transformation I want. I'm going to use that in different ways, so I could actually put that into a name and then use that with different transducers as well. So if I've got lots of different data and I have different algorithms as well, I can kind of do more complex things without making my code much more complex. Okay, so how do we apply this to the Advent of Code challenge? So we've got our fuel required, so we've got a function there, and then that's the same. We haven't changed that, but we can. So what we've been doing is mapping that field required over the puzzle data, and then we reduced it. So that hasn't changed, but we could then adapt this with using transducers. So we can generate sometimes like transducers are like the functions that you use, the algorithm that you use is referred to as xform or xf. It's just like a common alias for a transformation, because saying algorithmic transformation is quite a word for a handful. But here our transformation is quite simple, because all we're doing is just mapping fuel required function over our data. So that's quite simple. So we can just comp results of map fuel required over there, and then we just transform the data, and then we can reduce that by applying it to the data puzzle input. Or we could just write that in line as well. So we're essentially comparing this reduced statement with this transduce statement here. So in this simple example, there's not a huge amount of difference, but that's mainly because our transformation is quite simple. And the same thing for part 2 as well. We can here we again we've got quite a simple thing. We're just basically transducing puzzle data, but if we use so this is our loop recur function from the previous one, but we can actually break this loop recur function down into something a bit more functional. So here we've got the threading macro that's going to have several functions that are going to transform the data. So this is essentially our algorithmic transformation, our way to transform the data, and then we can apply that to particular data using transduce. So this is basically going to use iterate to apply the fuel required to each mass, and so we're using iterate to then get the mass. The result of that mass is the fuel we need for that mass, and then we're applying required fuel to that that fuel that we've just calculated. And so this is the same as doing this total fuel for module, and then we're just combining the results back together and reducing it up, so we get a single value for each particular module, and all the fuel, and the fuel for the fuel, and the fuel for the fuel for the fuel and the fuel. And then we can transduce that by using this map fuel delta over the puzzle data, and then adding up all of the results, and we get the same value there as well. So transducer is doing exactly the same thing, but we don't have all the loop recur cost, because it's going to be creating, if we go back to the loop, oops, sorry. So if we go back to this loop function here, we can see we're actually generating 3 local variables, and we're going to be regenerating them each time because we're doing a recur. So it's in terms of memory use, if we had like an absolutely massive data set, then, and we were doing more complex things here, then it would quite quickly use up more of our memory. So in this case, it is less efficient to use this loop recur compared to the transduce. Come on. There we go. Because in these approaches, we're not actually generating any kind of local names and so on, so it's more efficient in terms of memory and performance. and we get the same results. And then somebody did, I think this is a slightly different one I looked at, but essentially it's the same algorithm there. So that's the first one solved in two different ways. So using a very basic loop recur, and then also diving through into, we're using reduce, and we're using a transduce form, and we're also using iterate here as well. So iterate is replacing our loop recur and adding up all these values, and then we transduce it to apply it to all the modules in our data set. Okay, so I think there was some final thoughts. Yeah, so advantage of transduce over reduce in this example, probably not very noticeable, but in larger projects then it can increase the speed of memory and reducing like memory allocation for intermediate structures. That's why a lot of the Clojure functions in Clojure core are also reducing transducers. So if we look at map, let's make that a little bit bigger. Whee! Whoops, too big. So if we see, you can call map just with a function, and if we look at it, so like function so right at the last line it says it returns a transducer when no collection is provided. So in all the other ways of calling map, we've got these collections, so we can do multiple collections, we can do potentially infinite number of collections, but the first way we can call map is just by passing a function, which we've seen. So we could just do map inc and not include the data, and this would return a transducer for us. And if we look at the source code here, so if we just provide a function, so this is calling map with just a function, then you can see it's actually returning, it's calling it a transducer. It's actually, it is just a function definition, and that function can take 0 arguments or 1 argument or 2 arguments, and so on and so on, and multiple arguments. And it is just then it can then apply the results to basically apply the function to the results once it actually gets that collection. So we're not actually giving it a collection initially in here, but we return a function that will take a collection in, and once that function gets a collection, then it can give you the answer. Cool. There is some other, I'll put these in the show notes, but there's the transducers overview on clojure.org, and essentially it's this idea of building a pipeline. You've got whatever kind of functions you've got some input, and you get something out of it. With transducers, you got the same thing, except you can just do it, keep on doing it. You can have more complex algorithms in a very simple way. So it kind of walks through some nice examples of transduce as well. And obviously there's the transduce on Clojure docs, which have got some examples here. And there's a nice thing from Uswitch by Renzo Bogatti, who did another nice kind of like Clojure transducers with some exercises, I think, there as well. And that should give you a lot more practice with transducers. And there's probably quite a few things on there. I didn't actually have a look at this yet. But yeah, there's a whole bunch of other things on transducers. So there's lots of examples out there. Okay. There aren't any more questions. I'm going to leave it there. So thank you very much for listening. Again, just a reminder that we've got Clojure Bridge coming up in February. If anybody wants to volunteer, you don't really need to have a huge amount of experience with Clojure. Just need to be in London on the 21st and 22nd. That's probably the biggest requirement. And have a look at the learning paths to see if you can do that. If you have any feedback on how we've solved the advent of code things, please let me know, and feel free to go and start working on more of the puzzles as well. There's quite a lot to do. It does involve a little bit of time to do them all, but it is if you are looking for practice, then it's a great way to do that. And there's also on the Clojurian Slack channel, there's also a hash advent of code channel as well, where people have been posting their solutions as well. Okay, well, I'm going to leave it there, and thank you very much for listening as usual, and hope to see you next time. Thank you very much. Goodbye.